All right, so remember when you learned how to find derivatives? You first of all learned how to find derivatives of basic functions, right? You learned the power rule, and you learned how to take the derivative of e to the x, or the natural log, or sine and cosine, right? So, and then we learned how to find derivatives of more complex functions by using things like the chain rule and the quotient rule and the product rule. And so we're going to do the same thing with integrals, right? We learned how to find the antiderivatives of basic functions, and now we're going to start to learn how to take find integrals of not so basic functions, okay? And the first thing we're going to do is look at reversing the chain rule. Okay, so if you remember the chain rule, we have basically the derivative of a composite function. So we have an inside function and an outside function. And the chain rule says that if you have the derivative of f of g of x, you're going to take the derivative of f, all right, f prime of g of x, and multiply it by the derivative of the inside function. So you're taking the derivative of the outside function, and then taking it and then multiplying that by the derivative of the inside function. Okay, that's just the chain rule. So we're in this first example, we're going to apply the chain rule and then write the corresponding indefinite integral. Okay, so for this example here, we have a function f of x equals e to the x squared. Okay, so we have an inside function and an outside function. The inside function is the x squared, right? Inside is function is x squared, right? And the outside is the e to the x. So outside function is e to the x, or we could say e to the w, or whatever. It's the exponential there. So let's look at, first we want to use a chain rule to take the derivative of this, right? So f prime of x is just the derivative of the outside function. Now the derivative of e to the x is e to the x, so we get e to the x squared, right? We're going to leave the inside function inside, but we took the derivative of the outside function. And then we're going to multiply times the derivative of the inside function, which is derivative of x squared is 2x. Okay, so that's the derivative of e to the x squared. And so now, what does that mean, though, if we want to reverse that? What does that look like? So that's telling us that the indefinite integral of e to the x squared times 2x dx is equal to the original function that we just took the derivative of. It's the antiderivative, right? So e to the x squared and then plus c. Okay, so if the derivative is this, then the antiderivative, if the derivative is this, then the antiderivative is that. Okay, that's the original function. All right, so let's do some more practice here with this. All right, so the derivative of this function, right? Our inside function is x squared plus 1, and the outside function is this power of 6 function. All right, so if I take the derivative of this, and I've got a constant of 1/6, and then I'm going to take the derivative of the outside function, so I get 6 x squared plus 1 to the 5th power, right? Just using the power rule. Now I have to take the derivative of the inside function, again using the power rule, so I get 2x. And I can simplify that a bit, right? 1/6 of 6 is 1, so I can cancel those out. So I would end up with x squared plus 1 to the 5th times 2x. All right, so what does that mean? What's the corresponding indefinite integral? What that means is that the integral of the derivative, okay, which was x squared plus 1 to the 5th times 2x dx is equal to, write it down here, the original function, right? The function we took the derivative of. So 1/6 x squared plus 1 to the 6th plus c, all right? Because it's an indefinite integral, all right? All right, now I'm gonna pause here, and I'm gonna give you a chance to do these next two, because it's kind of the same thing. Just choose the chain rule and write the corresponding indefinite integral. All right, so I've done C and D now, and you can check your work. You notice here though that I didn't in part C, I did not put absolute value signs around x squared plus 4. And the reason for that is just that x squared plus 4 is always positive, so I don't really need them. Other than that, it should be pretty straightforward. If you take the derivative, then the antiderivative is the original function, right? So if we do if we take the indefinite integral, it's just the antiderivative. Okay, it's the thing you took the derivative of. So let's keep moving forward here and talk about the method of substitution. Okay, now you notice here that let's go back up here and let's look here. So you notice that we have these things going on. We have this 2x dx, right? And we have this 2x dx, right? In every case, we've got a quadratic that we're taking a derivative of. So the derivative of x squared is just 2x, and it doesn't really matter whether we had 2x plus 4 or 2x plus 1 or 2x minus pi over 2. The derivative is 2x. Okay, so you notice that notice that we have that derivative of the inside function times dx in every case. So the method of substitution, what you do is you try to recognize where the inside function is. Okay, what is the inside function? So that's the first part, is identifying what should be the inside function. And then we're going to do a substitution. We're going to call that inside function w. Okay, and then when we take the derivative of w, okay, we have this expression. This is written in Leibniz's notation, all right, but you can see that dw is equal to the derivative of w with respect times dx, okay, and then we're going to use that to make a substitution. So this will make more sense, I think, once you see it. Okay, we're gonna express the integrand in terms of w, including the dx. All right, so let's take a look at these examples. And the trickiest part is often just finding the inside function. So let's look at this. Now these are just exactly the same problems that we just did, just written in a different way. So now we're trying to find the indefinite integral of e to the x squared times 2x dx. Now you already know that because we did it back here, right? We found we found it. But if you didn't know that, what would you have to do to figure that out? So what we're going to do is we're going to let w equal x squared, right? Because it's the inside function of this first part, right? And so that tells us that dw, okay, we're going to take the derivative of this, and we get 2x dx, okay? Now notice this 2x dx, right, is right here, right? So we can make that substitution, and then the x squared is here, so we're gonna substitute w into x squared. All right, so when we do that, we get the integral of e to the w, right, because we defined w as being x squared. And if we define w as being x squared, then we can substitute dw for 2x dx, right? So 2x dx, that whole thing becomes dw. All right. Now that's an easy thing to take a derivative of. The derivative of e to the w is just e to the w. plus c, or the antiderivative. Did I say derivative? Yeah, the antiderivative of e to the w is e to the w. All right, and now we have the antiderivative, but we have it in terms of w, so let's resubstitute. And so that tells us, if we want this in terms of x, that's e to the x squared plus c. Okay, it's pretty clever. But it takes a lot of practice, and especially recognizing, okay, where's the inside function? And okay, but these should be straightforward because you can always check it. Go back to example 1 and you can check yourself. Okay, so here we let the inside function be w, so I'm going to say w is equal to x squared plus 1. So that's telling me that dw is equal to 2x dx. Okay, it's not always 2x dx, but in this case, they're all 2x dx. Okay, so now if I do that substitution, I get the integral of w to the 5th, and then this 2x dx here can be substituted. I can substitute dw. And so that's easy. That's just a straightforward power rule. So we get w to the 6th over 6 plus c. And now we just have to resubstitute. So I'm going to turn this over 6 into 1/6. And then we have w to the 6th. And w was x squared plus 1 to the 6th plus c. Okay, so there's our antiderivative. Again, I'm going to pause and let you try these next two, and then you can come back and to find the answers. Okay, so these are the answers you should have gotten for C and D, and I think it's fairly straightforward. Taking the you figure out what substitution you need to make, and then just do it, and then resubstitute when you get done. Again, you can see here I dropped the absolute value symbol because x squared plus 4 is always positive, so we don't really need it. It wouldn't, it doesn't hurt to have it. It's not gonna make it wrong or anything, but we just don't really need it in this case. All right, so let's keep going to the next problem. All right, so this one's slightly different. Not too much though, I'll tell you that. So again, we're going to try to identify the inside function, okay? And usually you're looking for an inside function where you can then, the derivative of the inside function is easily, you can also identify that as being in your integral here. So what I'm going to do here, I'm going to say let w equal, it seems like the obvious inside function is this t squared plus 1. Okay, and if we do that, we get dw is equal to 2t dt. Okay, now I'm seeing dt and I'm seeing t. Okay, I can rearrange this if I want to and say this is the same as the integral an integral of t squared plus 1 times t dt. Okay, so notice we have t dt, not 2t dt, but don't worry, we can fix that. Just divide both sides by 2, so we get 1/2 dw is equal to t dt, and t dt is what we need to substitute. Okay, so and t dt is 1/2 dw. So when we do the substitution, we get the integral of e to the w, but now t times dt is 1/2 dw. So 1/2 dw. Okay? All right, we can pull the 1/2 out front. We get 1/2, and the antiderivative of e to the w is e to the w, and plus c. And then we just need to then substitute w. So 1/2 e to the t squared plus 1 plus c. All right, no big deal. So let's take a look at, okay, I've got a bunch of just practice problems here. And so I'm going to do a few of them, and then I'll let you take over and finish these off. And then we have one more topic to cover, right? We've got, definite integrals. Okay, so I am going to do a couple of these, and then I'm going to let you take over and do some of the remaining examples, and then come back and check. Okay, so I mean, an inside function, outside function. All right, well, I'm seeing the square root function, and it looks like inside the square root function is this x to the fourth plus 5. So it seems like it'd be natural to just let w equal x to the fourth plus 5. All right, and then dw then is equal to 4x cubed dx. All right, now notice if I rearrange this, I can do this, x to the fourth plus 5. You don't need to do this every time. I just want to make a point that, you know, what we have is x cubed dx. Okay, and we want to substitute that. But here we have 4x cubed dx, so divide by 4 and we get 1/4 dw is equal to x cubed dx. All right, now we can do our substitution. So this becomes the integral of the square root of w, which I can write as w to the 1/2. I don't necessarily want parentheses. I'm just going to write w to the 1/2. That's the same as the square root. I just like it because then the power rule, or the reverse power rule, works nicely. And then x cubed dx is equal to 1/4 dw. Okay, now I'm going to pull the 1/4 out front. Okay, and then the antiderivative of x to the 1/2. Okay, so I'm going to get w to the 1/2 plus 1, which becomes 3/2, all over 1/2 plus 1, which is 3/2. Okay, and then we have plus c. And if we simplify that, I get 1/6, because 3/2, the reciprocal of 3/2 is 2/3, and then one of the 2's cancel. So if we simplify that, we get 1/6 w to the 3/2 plus c. And then we just have to resubstitute. Our w is, so we have 1/6, oops, but that'd be a parenthesis, and we substitute w is x to the fourth plus 5, and then to the 3/2 plus c. Okay, so that's our final answer. All right. The next one, we've got, that looks like, you know, we've got a reciprocal function, right? 1 over something, but then we also have this t squared. So I can combine, I think what I'm going to do is combine that, and then I'll have 1 over this 1 plus t cubed. So 1 plus t cubed is my inside function. So I'm going to let w equal 1 plus t cubed. So dw is equal to just 3t squared dt. Okay, but again, I have t squared dt, not 3t squared dt. So if I divide by 3, I get 1/3 dw is equal to t squared dt. Okay, so now let's do our substitution. So we get the integral of 1 over w times 1/3 dw. Okay, and we can pull the 1/3 out front, and then we have the natural log of w. Okay, plus c. So that's our antiderivative in terms of w, and now we just have to write it in terms of x. So natural log of, and now this time I do need to preserve the absolute value. So 1 plus t cubed, because this can be negative. So I need the absolute value symbols here. Okay, so there we go. All right, how many are left? Let me look here. There's like 3 more examples left, and I'm going to let you do the next 2, examples 6 and 7, and then I'll meet you back up for example 8. All right, so here are the answers for these next two. These were slightly more difficult, but not too bad. I guess they involved trig functions, so but still, you're just looking for an inside function and an outside function. So, so there's the answers for those two. I don't know if there's anything it's pretty straightforward, I think. So let me know if you have any questions when we meet for office hours. So one more example I'd like to go over, and this one, it's sort of an exception, so I want to go over this one with you. Now, what I'm seeing is 1 minus z, and that whole thing squared. So it seems like maybe 1 minus z is an inside function to the x squared function. But if I say, let w equal 1 minus z, then dw is just equal to minus 1 times dz. And I've got z to the 4th and dz. I don't have minus 1 dz. So this is one where substitution doesn't really help. All right, so substitution doesn't help. Here. So we got to figure out a different approach. Now, this is what, this is also they say that if all you have is a hammer, everything looks like a nail. So in this case, our hammer, our substitution, doesn't really work. But you know how to do this problem. And what you have to do is just expand this out and make it into a polynomial. Okay? So I guess the warning here is that, you get used to doing substitution, and then suddenly you go back to a problem that you really already knew how to do, and then you're trying to apply substitution to it and it doesn't work. So all right, so let's expand this out. So I can take 1 minus z squared. So let me write z to the 4th, and then this, if I expand 1 minus z, I get 1 minus 2z plus z squared. Right, I'm just expanding it out, dz. Okay, and then I can also distribute the z to the 4th. So I'm going to get z to the 4th minus 2z to the 5th plus z squared times z to the 4th is z to the 6th. Okay, dz. And that's just a polynomial, right? So we can apply the reverse power rule to this. So we're going to get z to the 5th over 5 minus 2 z to the 6th over 6 plus z to the 7th over 7 plus c. Okay, don't forget your plus c. Now this could be simplified a little bit because I can make this into 3. So I get z to the 5th over 5 minus z to the 6th over 3 plus z to the 7th over 7 plus c. Okay, so there you go. All right, so now this last thing that we're going to talk about is just how we can evaluate definite integrals using the substitution rule. And it's pretty straightforward. If you can find the antiderivative, right, then you can find you can evaluate it using the fundamental theorem of calculus, right? So let's first of all just we need to find the antiderivative, which is the thing we've been doing. So find the antiderivative. Okay. So I need to figure out what the inside function and the outside function is. So I'm going to let w be equal to x squared minus 4. So that tells me that dw is equal to 2x dx. And now I have x and dx, not 2x and dx. So I'm going to write 1/2 dw is equal to x dx. Okay, and now if we evaluate this, if we just evaluate to find the antiderivative, right? So I'm going to take the integral of x squared minus 4 times x, oops, that's cubed, right? I'm just going to move the x over by the dx so you can clearly see the substitution I'm making, and that is going to give me w cubed times 1/2 dw. Okay, and we're just gonna, we can find the antiderivative in terms of w. I'm going to pull the 1/2 out in front, and we get w to the 4th over 4, and then plus c. Okay, so basically, well, let's write this now in terms of x. All right, so we got to resubstitute for w. 1/2 times 1/4 is 1/8. And then we have x squared minus 4, that's our w, to the 4th plus c. Okay, so we got the antiderivative. Now, and now we've got it also in terms of x. So now it's pretty straightforward. It's pretty much what you expect. If we want the, let me write it over here, the integral from 2 to 3 of x times x squared minus 4 cubed dx, right? That's what we're trying to find. Now that I know the antiderivative, I can just evaluate the antiderivative. So x squared minus 4 to the 4th, evaluated from 2 to 3. So, and then it's just a matter of plugging in the upper and lower limits. So we get 1/8, and if I plug in the upper limit, I get, so that's 3. 3 squared is 9 minus 4 to the 4th, okay, minus 1/8, and plug in the lower limit, and I get 4 minus 4 to the 4th. Okay, now that's just 0, so I'm going to get 5 to the 4th, 5 to the 4th all over 8, which means 625 over 8. Okay, so that's my final answer. That's my definite integral. But there's another way that I want to show you that you could do this. If you don't, you can actually take the antiderivative, take this antiderivative, which I could rewrite as 1/8 of w to the 4th plus c, make it a little nicer. And I don't have to convert it back to the x variable. I can actually evaluate the antiderivative in terms of w if I convert my limits of integration. So I'm going to show you that alternatively. So we have to convert the limits of integration. We can convert the limits of integration. Okay, so let me show you how you can do that. So when x equals 2, what is w? Well, w is x squared minus 4. So then w is equal to 2 squared minus 4, so w equals 0. And also when x equals 3, okay, that's our upper limit of integration, we can then write that in terms of w, because w is x squared minus 4, so we get, so w is equal to 3 squared minus 4, which is 9 minus 4, which is 5. Okay, so if we want to evaluate the definite integral from x equals 3 to x equals 2. Sorry, the lower limit is 2, the upper limit is 3. X equals 2 to x equals 3. Okay, now normally we don't write the x equals for the limits of integration, but I'm just trying to make a point here. This is what we're trying to integrate, right? It's x squared minus 5, minus 5, right, minus 4. I wrote minus 5 in my notes for some reason. All right, it's minus 4 cubed dx. That is going to be the same as integrating it with respect to w. So w equals 0 to w equals 5. Okay, and then we can just integrate the original, the integral in terms of w. So we have w cubed times 1/2 dw. Okay, so we can just evaluate it straight away without having to go back and forth between x. So we end up with, this is 1/8 w to the 4th, right? And we can evaluate that now from 0 to 5, right? Because we've converted our limits of integration to w and not x. And when we do that, we get the same thing. We get 5 to the 4th over 8, which is 625 over 8. Okay? So I just wanted to show you that alternative way. So it just might save a step of having to convert back to x. But you still have to evaluate the, those limits of integration and convert them to w, the values that they would be, that w is at those values of x. Okay, so that's what this box is saying here. It's just reiterating what I just did. There's two ways that you can evaluate definite integrals when you're using substitution. You can convert back to the original variable, or you can leave things in terms of the new variable and convert the limits of integration. Okay, so next thing I have is just some practice problems. So just like everything else, it's practice, 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 and you'll be a pro in no time. So we'll talk to you later.